This is a demonstration of confidence intervals and why they work. We're going to start with our basic assumptions for the reasons that we do statistics. And we wish we could do a census, but usually it's not possible, so we have to take a sample and we have to use that information to draw some conclusions about the whole population. So a confidence interval is this range of numeric values that we think actually contains the parameter, such as mu, the mean of the population. If we wanted to create a 95% confidence interval and we repeat the same sampling process many times, then about 95% of the intervals that we create would contain mu and about 5% wouldn't. But of course, we don't repeat it many times, we just do it once, and we hope ours is one of those that contains the parameter. Be various software products used to show this demonstration, including Microsoft's Excel, an Excel add-in called Resampling Stats, and Statistica. What we're going to do is start with 20,000 quantitative values that will not be normally distributed, and we're going to consider this to be the entire set of data. And from this, we're going to select 50 numbers and find our sample mean. And this is going to be our mean, the one that we would have gotten if we only did it once. But then just to show how what we get is one of many possible sample means we could get, we're going to do 9,999 more selections. And we'll see where ours fits into the whole picture. And then we'll compare the sample results to the original data based on the central limit theorem. It says the mean of all the sample means should equal the mean of the population, and the standard deviation of all the sample means should equal the standard deviation divided by the square root of n. We're going to generate data. We're going to do 20,000 values and put them all in one column. And we'll start at 1, and we'll go up to 100. And this is the distribution that will come in each of these 7 sections, just as a way of making it skewed. And notice you see the row numbers going up, and they will eventually stop when we hit 20,000. Right there. So that's our original data. Now, from this data, we're going to make what is considered our selection. So we're going to sample with replacement, and our input range will be those first 20,000 cells. Our output range will be cell C1, and we're going to take 50 in our sample. And there's our selection of 50 values. And now we will find the mean of these 50 values, so equal average, parenthesis, and we'll select all those values. And so the mean of our sample, so sample mean is 37.406. Our sample standard deviation, let's see, I'm going to just figure it out here, is equal to STDV, and we'll do it for this data. And now I just want to copy and paste that value in there. And now we can delete this. Now, our population mean is equal average 39.84. That's the number we'd really like. Notice in our sample we got a 37, so our sample mean didn't equal the population mean, which is typical. And our population standard deviation is equal to TDVP and that's our population standard deviation. All right, so this is our actual value, but now we want to see what other values we could have gotten from this data. So we're going to repeat the sampling process, and we're going to do 9,999 other trials. And while this is going on, I'm going to shut the recording off because it takes a little while to get through, and we'll return when we get through it. Before I do it, notice down here in the corner the counter of how many values we've gone through. We're nearing the end. These are all new sample means, and it took us 59 seconds to do that. And we can look at the results on the results sheet down here. And if we scroll far enough down, we get to our 9,999 value. And now what we're going to do is go back to the data, and we're going to copy and paste our actual result into this list. So now we have 10,000 different values. And now what we're going to do is graph the original data by going into Statistica. So we're in Statistica, and we're going to open a new file that's got two variables and 20,000. Okay, 20,000 cases, and we'll make variable 1 be original data, and variable 2 can be sample means. And we can jump back to Excel, and we can copy the original data and paste it into Statistica. And then we'll get our sample means. Notice it includes our mean, the one we got for our sample. And we'll paste that in here. And now what we'll do is we'll make a histogram that includes both of these. So we want to do multiple, the original and the sample means. And it'll be fit with a normal curve. And here's the data. The blue data is the original data. Notice it's skewed and definitely not normal. And it's hard to tell whether the sample means is normal or not. So what we're going to do is make another graph, but we're only going to use the sample means, and we're going to set our boundaries. It looks like we should be able to do between 30 and up to 60 maybe. So we'll do boundaries, and we'll specify boundaries starting at 30 and going by 2s, and maybe we'll go max to 60. And so here's what we see is the sample means are normally distributed. And if we look close enough at it, let's compare. Notice the mean of the original data and the mean of the sample means are quite close to each other. And then the question becomes, how does the standard deviation of the original data compared to the standard deviation of the sample means? If we take the standard deviation from the population that we found in Excel divided by the square root of 50, we get a standard deviation of the sampling distribution of 3.32, which is close to the standard deviation of the sample means that we got from Statistica. Now what we want to do is see how all this works with the formula. The formula starts with the sample mean. It adds T star standard errors, so standard deviation over the square root of n. So this will come from our sample. This will come from our sample. This we will look up on Excel, and this will be 50. To find the T star value, we will use the formula and insert a function, and under statistics, statistical functions, we'll do T inverse. So this is a probability associated with two-tailed students t distribution. So we're going to put 0.05 here. It's out on the tails if we wanted to be 95% confident. We have 49 degrees of freedom. And so we get a t-value of 2.0095. Now we're going to substitute the sample mean, the sample standard deviation, and the t-star value into the formula. And here you can see the substitution. Now this is the margin of error, everything to the right of the plus or minus sign. So when we find the margin of error, we find it 6.323. So this times that divided by the square root of 50 gives us that. And then our confidence interval is between 31.079 and 43.725. That is, we took 37.406 and subtracted 6.323 to get this number, and then we took 37.406 and added 6.323 to get that number. Now, is our true mean somewhere between 31 and 43? It is indeed. So we see that the true mean was 39, and that fell within that range. Now, let's for a moment go to the results section. We're going to sort all the results in ascending order. And so if we want to use the resampling method to find the confidence intervals, then what we can do is eliminate the bottom 2.5% of the values. So we'll eliminate the bottom 250 values. Let's make them a different color. And we'll eliminate the highest 250 values. Get our counter there to be at 250. And then the borderline values will be part of our confidence intervals. So we've got one value as 46.52. And when we move it up, we can see that the lower boundary is 33.426. And so 95% of the values are in between there, and this is a different way to find the confidence interval, although not one that we can do in class because we don't have the software. But notice the true mean falls somewhere in between there. And here's the true mean, which falls in between those two values, and here's our sample mean. It's a good estimate.